Good morning, good afternoon. Welcome to today's webinar, From Materials to Module Assembly, Applications of Automated Visual Inspection in the Flat Panel Display Supply Chain. My name's Kathy Macbeth. I'm the Marketing Manager here at Radiant Vision Systems, and I'd like to start by thanking you for taking the time out of your busy schedule to join us today. Hosting today's webinar is Eric Eisenberg, Radiant's Applications Engineering Manager. Eric has spent a lot of time in the field developing and implementing automated visual inspection solutions at multiple points in the manufacture process. He has extensive hands-on knowledge of this topic. So whether you are a brand owner or a supplier to the industry, I have no doubt that you'll come away from today's presentation with some very valuable information. Well, before we start, just a couple of housekeeping items to let you know of. You can submit a question to Eric at any time during the broadcast. To do so, just type your question in the questions pane that is usually going to appear on the right-hand side of your screen and press send. As I mentioned, you can send that at any time. However, all questions will be answered at the end of the presentation. So I know we have a lot of material to cover in a relatively short amount of time, so without further ado, I'm going to pass the microphone over to Eric Eisenberg.
Great. Thank you, Kathy. Thank you for the warm introduction. Welcome to today's webinar. My name is Eric Eisenberg, as Kathy mentioned, and we'll be talking about automated visual inspection of flat panel displays and the flat panel display manufacturing process. So today's agenda is going to cover automated visual inspection, the flat panel display process, and then various applications for automated visual inspection in various points in the manufacturing process. And then we'll have a brief summary and questions and answers period. So we're going to start with automated visual inspection. What is automated visual inspection? Well, over the last 10 or 20 years, the requirements for display quality have increased very dramatically. And as a result, visual inspection has become a really key part of the measurement or of the process of actually manufacturing flat panel displays. So we have found that many aspects of the flat panel display process, manufacturing process, have become automated, and one of the last parts of the process to receive a significant amount of automation is visual inspection. So with the requirements increasing in quality all of the time, the requirements for the visual inspection have also increased. That requires higher training, more personnel, and larger amount of investment for the brand owners and for the supply chain in order to produce quality product. So what is the solution? Well, what our recommendation really is that you can automate visual inspection systems. Throughout the last few years, we've seen a significant growth of automated visual inspection in the assembly line. And the technology has improved to a point now where it really is viable to replace human operators working as visual inspectors with automated visual inspection systems. Now, one question that is very common is what are the benefits of an imaging colorimeter versus what might be considered a traditional vision system or machine vision type system. Machine vision system is very good for a high throughput production line where something very simple is being characterized, like the color of a bottle or sorting pills or something along these lines. Imaging colorimeter is specifically designed to mimic the response of the human eye. And what we are really trying to do is essentially create a robot eye that can do the same work that a human visual inspector would typically do, but do it extremely repeatably and consistently. So we have color filters in the imaging colorimeter that mimic the color response of the eye. There is a very high dynamic range of the detector and very low noise, which is a real difference compared to what we would see with a machine vision system, which might be quite noisy and also typically does not have a very high dynamic range, unlike the human eye, which has an extremely high dynamic range. We also include built-in color calibrations for luminance and for color to make sure that the results from the system match the international standards for CIE, for color coordinate, and for luminance, and so that is a traceable standard and can be reproduced at multiple locations and with multiple instruments, all calibrated to the same standards. There's an extremely high repeatability factor. When you take a measurement with an imaging colorimeter, you get the same thing every time. One of the ways that we ensure that is by cooling the sensor and maintaining the sensor's temperature very consistently so that we get the same answer every time when we take a measurement of the same device. There's certainly a lot of flexible lens options for various fields of view and different working distances. And then you can have multiple resolution options, and all the way up to 29 megapixels is available in the industry. Depending on the resolution of the system that you're trying to inspect, the resolution of your imaging system is going to scale as a result. It should scale. And then we have intuitive software that creates a good interface for analysis, and then also a very simple interface for production environments for operators to interface with, if that's even necessary. And then also a fully programmable interface and analysis so that we can fully integrate the system into an existing production line or create any kind of interface that's required for the customer's application. And then Radiant Vision Systems is very proud to offer world-class service and support worldwide. So what is a typical automated visual inspection system consist of? And that would consist of a imaging colorimeter, whether it be a colorimeter or a photometer is just dependent on the application. If color is not important and all we're looking at is contrast of the device that we're measuring, then a photometer would be sufficient. A software package, which would include some kind of automated visual inspection algorithms. In this case, we're talking about TrueTest, which is an automated sequencing software that Radiant Vision Systems offers, which can automate testing for visual inspection. Also a PC, which is required for running TrueTest. And then you would also have potentially a fixture associated with the setup that would potentially be required for the application. The fixturing is something that we often do ourselves, and we also work with various suppliers and customer fixtures to interface with those. And this inspection can be done both online or offline. We offer comprehensive testing options. There are a lot of different software algorithms available within the TrueTest package, and then many that are developed on a case-by-case basis for various types of MURA and other defects that we identify in the field when we are working with the devices with our customer specifically. But a typical application would be something like uniformity testing, a defect detection algorithm. In this example, you can see something which looks like a blob analysis and line MURA. Both of these tend to be common defects that we would encounter in the flat panel display process. And then also we mentioned MURA detection here. For those who aren't familiar, MURA is a Japanese word which most closely translates to blemish in English. Essentially, it's any kind of local non-uniformity which is visible to the human eye and would be undesirable in a finished product and something that we would like to detect and quantify. So what are the benefits of doing automated visual inspection in the FPD supply chain? The big benefit is going to be improved quality and brand perception, fewer returns, and decreased labor cost. Basically, if you can find these problems before they make it to your customers, that will improve the perception of your brand and improve the quality of your product and produce higher and more consistent results. Decreased labor cost. I've seen examples of potentially one system replacing up to 13 human visual inspectors. The camera does not get tired. It does not produce different results. It works consistently around the clock and gives the same answer all of the time. What are benefits in the upstream manufacturing? And what we're going to talk about next is essentially the entire TFT process and the production process and the various points where we can add visual inspection to improve the entire production system. And what this will end up doing is reducing the amount of scrapped devices. It reduces the it also allows you to track trends in the process if there's some kind of defect which has appeared from a certain batch or after tweaking a process that can be identified and quantified, and then again decreased labor cost. So we have applications for automated inspection in the flat panel display supply chain. So before we talk specifically about these applications, we need to talk a little bit about the flat panel display manufacturing process itself. Specifically today we're going to be discussing the thin film translator process, and to assemble a final assembled LCM or a assembled flat panel display requires a few components. The main components are the backlight unit, a cell, and which then becomes the liquid crystal module, which will then be packaged into the assembled device. This slide shows that there is an opportunity to do both outgoing and incoming quality assurance at many different points in the assembly process. Essentially, the sooner you can find a problem in the assembly process, the more money is saved in reduced scrap and improved quality. Specifically, the backlight unit, the cell, and open cell, and the LCM are all points where significant amounts of human inspection are done. And inspecting the film, glass, light guides, and even the LED assembly are all options that can be done to improve the overall quality of the product and streamline the assembly process. So let's talk specifically about backlight inspection. The backlight unit is an LED assembly and a light guide. Light guide or diffuser, some kind of essential Lambertian surface which will diffuse the light and make a uniform illuminator for the liquid crystal module. Essentially, the backlight unit is the only device that illuminates the flat panel display, and any non-uniformity or undesirable effect that is present in the backlight unit will propagate all the way to the flat panel display itself. So typical things that you might see as a problem with a backlight unit is the uniformity of the backlight unit itself. There's an effect known as light leakage, which will appear and is seeded by a failure in the backlight unit production. And then particle and fiber detection, fiber just meaning dust fibers. All of the factories where the backlight units are created are generally done in clean rooms, always done in clean rooms. However, clean rooms are not perfectly clean, and even in a very clean environment, particles and dust can be introduced into the process and potentially be embedded in the backlight units themselves, which may result in a scrapped unit. And also the backlight units are handled as they move around the production line, and that can introduce scratches, and those should be inspected, and if they're present, they need to be detected. So what are common issues that you would see with backlight units? What are the kinds of things that our customers might be asking us to test? We have a couple items. Light leakage is a big one, and uneven colors. Yellow MURA, often there can be a yellowing that appears in the backlight unit. Another item that isn't mentioned here is the white balance of the backlight unit. It may be important to inspect the color of the backlight unit, because the white color that is produced by the backlight unit is the white that you will see when you're running the flat panel display. So what is the solution to these potential common issues that you might see with a backlight unit? We can do defect detection with TrueTest using what our uniformity test and also potentially the particle defects test. And in this case, we're recommending a Prometric I16 imaging colorimeter. And the reason behind that is the imaging colorimeter is necessary so that we can measure the color of the device if we're looking for yellow MURA or white balance. And also, backlight unit production tends to be very high volumes, and a very rapid takt time is required. However, the resolution of the measurement system doesn't tend to be so critical because the TFT is not present on the device. The reason we're recommending the I16 in this situation is that we have a feature in the software of TrueTest known as multi-channel, which allows us to measure multiple devices simultaneously. And so we have seen applications where we can measure 4 or even more backlight units simultaneously with the single device in a single shot. So what are the benefits to using the automated visual inspection on a backlight unit? It's really worthwhile to find a problem in a backlight unit before it makes its way further along the flat panel display production process. Any kind of defect that might occur in a backlight unit is going to be very visible and present in the flat panel display. And backlight units are very inexpensive, and scrapping a backlight unit that is bad is a much more desirable situation than allowing it to make its way through the process and having to scrap a more complete module. We also need to do inspection of raw materials, and so there's an opportunity to do this. When the TFT array is being fabricated, it consists of both glass and film that's deposited with a photoresist process. We can essentially inspect every aspect of the glass and the film both on an outgoing and incoming basis to the factory that's creating the TFT array. Glass and film can have particles. It may have some kind of non-uniformity, a MURA, a local defect that isn't quite a particle, but maybe a difference in the thickness of the film, and also cracks. Glass can crack, and we can detect that. So a typical inspection of glass or film would be looking for things like particles, MURA, and cracks. And how would we do the inspection? Again, we would use the TrueTest software, but this time specifically the particle defects test would be the test that we would be interested in, looking for any kind of particles, any kind of larger blobs, and then a crack would show up as a very strong local contrast variation. And for this application, we're recommending the Y-series photometer because color is not really a concern for the film or the glass process, and the Y-series can save a little bit of money, and then also it just tends to be much faster than a full color system. And what are the benefits of using automated visual inspection in this process? Basically, just ensuring that the component meets a standard, and it can reduce the rework costs by identifying problems early in the process before you go further down the line. We also recommend doing inspection of the cell assembly. So what is a cell? A liquid crystal cell in the nomenclature that we know consists of a TFT array, which is an array of transistors that affect the liquid crystal that's filled into the cell, and a color filter, which is specific for each different pixel so that we have subpixels and we can turn on various colors at every pixel location. We also have a device known as an open cell, which essentially is the cell but sandwiched between polarizers, and typically there's a PCB that's attached to the open cell as well. So for inspection, open cell is a little bit more desirable because the polarizers are already present. The interface is more straightforward as far as how we would control the device before while we're inspecting it. But cell inspection is also a possibility as well. But there needs to be a few different extra components added in order to make that possible. So let's look at what are common issues for cell assembly. Basically, at this point of the assembly process, takt time is really important. Any kind of false defects on polarizers, the BLU, and cell surfaces can introduce some overkill. It's possible that there might be dust that can be wiped away or something along these lines. We have methods that can reduce that aspect, but typically our customers are more interested in avoiding escapes rather than having a small amount of overkill. So typically we're asked to operate on the side of having a small amount of overkill rather than any number of escapes. In this particular application that we're talking about here, it looks like we're talking about using two Prometric i16s and TrueTest software that can communicate with a host, the pattern generator, and the fixture, host being the factory, either the MES system or some kind of CIM system. And two i16s are required for this application because the resolution of the device is very high. And it's not absolutely necessary that we stitch images together, but we can inspect multiple halves of a device in order to get the resolution that's required for the type of defect detection that the customer is asking for. And the quality of the cell is ensured as the assembly moves to the next step of the manufacturing process. And also, some defects that can be detected at this point in the process actually can be repaired. So there's an opportunity potentially to create a pixel map where you can identify specifically where some of the defects are located. And finally, we have the liquid crystal module, which is the final step of the assembly before we get to the packaged device. Again, we can look for all of the same problems that we were looking for at every step of the process, and new problems can be introduced as the devices are put together. What are common issues for the liquid crystal module? MURA tends to be the most common problem at this point. Most likely any kind of particle defects or something like this would have already been scrapped and removed from the process. But in the part of bringing everything together, the polarizer can become deformed. There's a number of different things that may occur that will appear as some kind of blemish that should be quantified. And so the solution in this case is using some kind of relatively high-resolution imaging system. Again, the MURA algorithm that we have can detect blobs in MURA and give a specific J&D value. Again, a really good aspect of the automated visual inspection system is the fact that we can quantify defects repeatably in a situation that tends to be very, very objective and subjective for how the operators would potentially view the system. And then cell quality can be ensured as the process moves to the next process. And then also some of the defects in this point can be repaired. So we have the final assembly where we actually add the glass and assemble the device. And again, some inspection can be done at this point. We have a completed unit, and it looks very beautiful. So in summary, we talked about various applications for automated visual inspection in the flat panel display supply chain. Backlight unit testing is a very good and straightforward example of how this testing can be done. Raw materials can be inspected. The various points of the assembly can be inspected both on an incoming and an outgoing basis. And then final assembly quality assurance can be done, all with automated visual inspection. So we like to implement this at key points of the display manufacturing process, imaging colorimetry based on systems to ensure quality, improve process efficiency, and reduce costs for both brand owners and their suppliers. Thank you very much. And now I open up to questions. Okay, we're looking at some questions that we have available. I see one that says, is autofocus available? Autofocus is not specifically available. However, we do have software controllable lens systems. And in that case, what we do is we can repeatedly change the focal length to a specific value consistently. One problem that we had seen in past systems is operators will be responsible for focusing or potentially even slightly defocusing optics, and the inconsistency of the operator's action reduced uncertainty in the measurements. So having a software controllable lens where we can repeatedly set the focus of the lens every time is something that's quite useful. I see a question about a conoscope and lenses, and there are some other products that we have in our product line, like the ISSA, which could potentially replace the conoscope. So that would be something that you would want to consider, and we could certainly talk with you about that. I see a question here about contrast ratios in addition to J&D values. That's a great question. Absolutely, we can use contrast ratio in addition to J&D. One thing that tends to be a little difficult for customers to understand sometimes is the fact that J&D is not the end-all be-all of quantification of MURA and defects. Often what we really want to do is try to match exactly what a human inspector looking at the same device would respond to. And the J&D value doesn't always necessarily scale to what the human inspector might say. The human inspector is often required to grade an entire display rather than individual defects. And so often we have to come up with some kind of algorithm working with the customer, specifically using contrast ratios of the defects, potentially J&D values of the defects, and combining all of that input into something that looks like it matches what the humans are seeing and what the humans are reporting. So how much time do we have?
We've got time for just one or two more questions.
Okay, one or two more.
Okay.
All right, I'll take an easy one. I see what does J&D stand for? That is just noticeable difference, and that's a standard that's defined in a few different places. One is SEMI, S-E-M-I, and so if you look up SEMI and J&D, you can find some standards that are defined based on that. And another good one here, and I guess this will be the last one, is can view angle be measured with the system? If so, is this the best type of tool and how would it be implemented? Similar to the other question about the conoscope, we have a device which is a large sphere which essentially simulates the conoscope, and that can actually look at luminance or color as a function of angle, so that is an option. Another thing that's worthwhile to mention is that view angle tends to be a fairly strong effect in flat panel displays, and we have various calibrations, one specifically called a multi-point calibration, which helps us remove the effect of view angle from the measurements. So a measurement of luminance or color looks the same as it would be if we were measuring normal to the device with an imaging photometer or a colorimeter, something along these lines. Hey, thank you everyone for your time. Appreciate it.
Okay, thank you so much, Eric. We actually got a lot of questions, which is fantastic, but we do want to be respectful of the time allotment that we've provided for this. So we will follow up with those of you who submitted questions that we didn't have a chance to answer via email. A lot of people asked about the availability of this presentation afterwards, and it has been recorded, and we will be providing you with a link to the recorded version as well as slides, and you should see an email within a week's time for those. So once again, thank you so much, and enjoy the rest of your day.